Hello, in this video, I wanted to share with my experience on how I would create a fault tree. So as an example, I wanted to go through a walkthrough that was provided by this document that was created by NASA. It's called Fault Tree Handbook with Aerospace Applications. And if we go to the example that was described in this document, it's called a monopropellant propulsion system, and it shows a schematic that consists of two parts. The first part on the left is an electronic circuit that consists of switches and relays. And the second part on the right is a mechanical subsystem that consists of tanks and valves. So the next page shows the possible states that the system has to undergo in order to produce its function. So quickly, the modes are the dormant mode that transitions to the armed mode, which transitions to the thrust mode. And then it branches to either back to the dormant mode or it goes to the emergency shutdown mode. And then finally, this example lists the final fault tree output. So in this output, we see that the top undesired event has a description: thruster supplied with propellant after thrust is being cut off. And what we want to do, we want to reproduce this example through actual modeling. And I had done this by using a special tool called GSI Express. Now, quickly, GSI Express is, in my opinion, a very powerful tool that lets me create fault trees through topological modeling. And I can do that by using their diagnostic framework, which will then generate fault trees for me automatically. So as a first step, what I had to do, I had to recreate the topological model that was given in the NASA example. As you can see, this is the this is the topology that I recreated, but then I added some minor changes. I added 3 input flags and 1 output flag to the components. So the first input flag, as can be seen, is being connected to the arming switch S1. So this is in case when S1 is being pressed, it will output its function. And then the second input flag is connected to the inert gas pressurization tank, TK1. So this inert gas pressurization tank, it stores inert gas, which is then being transferred down the chain. And then finally, it's being converted to thrust. And then the third output flag is connected to the emergency cutoff switch S3. It's in case when S3 button is being pressed on, it will stop thrust being produced. And then finally, the one output flag that I have added, which is here, it's added to the thrust chamber inlet valve, IV3. This is where the inert gas is being converted to thrust, and then thrust is being produced as a final output. So as we had seen, the example listed several object states for each component. And so what I had to do, I had to model the same thing that has been shown in the example. If, for example, if we go into the arming switch S1 and I click on states, we see the 2 states that this particular object has to undergo. So for instance, we see that I inputted object state open, which is the default state. And then the second object state is momentarily closed. And I have to do this for each, I have to specify the states for each of the objects. For instance, if I choose K1 relay, It shows that relay is in the closed state, closest state, open or opens, and so on. After creating object states, what I had to do, I had to create test sets. So as can be seen, I created two main test sets. One is normal and the other one is emergency set. So the normal and emergency set, they have listed modes, and the first five modes are the same. So they're dormant, transition to armed mode, transition to thrust mode, and thrust mode. So as can be seen, there's all the same descriptions for both sets. But then after the thrust mode under the normal set, we have transition to dormant mode, and then finally dormant mode. And for the emergency set, after the thrust mode, we have transition to emergency shutdown mode, and then emergency shutdown mode. So basically what I had done, I reproduced the branches that were shown in example. And so if we uh, go into this model, if we double click on one of the sets, for instance, the normal set where I have described as closed circuits and open valves. That means, like I modeled this set as active components. If I double click, we can see how the signal propagates in each mode. So we see that the signal propagates from active components, and the active components are being highlighted in green. So in here, we see three active components because they output their functions through these pink lines. And these pink lines are being transferred through the output ports, which are red dots. So the output ports, the output functions are being transferred to the, like next objects that are being connected to the import ports, which are green dots. So for instance, we see that this particular object is being gray, so it's inactive. So in this inactive state, it can only receive functions, for instance, from this component and from this component. But because it's inactive, it does not output any functions on its own to other objects. So, and then as a final, observation, we see that in this particular mode, dormant mode, no thrust is being outputted. So if we cycle through, we see how the states are being changed. So for instance, in this particular state, we see that the switch S1 is being activated. When it becomes activated, it sends the signal to this object, which deactivates it momentarily. And because this object is being deactivated, it activates this object, which sends its signal down to the chain. And then if we cycle through a little bit more, we see that in the thrust mode, thrust is being produced. And then we see that once it transitions to dormant mode, thrust is not being produced. So if you remember in the example, we want to model the undesired event of thrust being produced while the command is being given to for the system to stop producing thrust. So in this case, we're interested, like in this state of the system when it transitions to the dormant mode. Specifically, we want to model the undesired event of thrust being produced when it shouldn't be. And so in order to input this undesired event, we we go back to the design and we go to the failure effects. And under the design failure effects drop-down, we specify this description, which is continued system firing after the system has been commanded off. Once we input this description, we can then run the Famica and generate the fault tree, which I had already done. So if I go straight to the Famica and then I generate the fault tree, I see that the top undesired event has this same description: continued system firing after the system has been commanded off. So once we have created the top undesired event, we go back to our topological model and we try to identify causes that would contribute for the thrust to be produced in this, like in this mode. So as you remember, in order to find causes, for the fault trees, they have to be immediate, necessary, and sufficient. So in order to identify this immediate, necessary, and sufficient causes for the fault trees, what I had found useful is to create a diagnostic studies. So I created two diagnostic studies. One is called normal and the other one is called emergency. If we go to the normal diagnostic study, as you can see, I had created in this study 3 test sequences. The test sequences are thrust mode, transition to dormant mode, and the final test is the dormant mode. And so what I had found useful in this tool, it's a very useful feature that is present. It's called desktop fault insertion. So after I had created this test sequence, what the system lets me do, it lets me automatically create fault groups. So after creating those fault groups, when I click on a desktop fault insertion, I can then insert faults. I click on the insert button and then click insert. And then I choose this IV3 component. This is the component where thrust is being produced. So it's immediate, necessary, and sufficient. So because it's immediate and it's necessary, we want to find, whether this is there's a sufficient cause. So if I click OK, and then I click on diagnose fault, it shows, it shows me where, in which fault group this IV3 component is located. And it also identifies other components. And this other components, I can inspect whether, this components are necessary and sufficient for the causes for the thrust to be produced. So if I close out of this window and then I go back to the topology, I see all of the suspects that can be included for my fault tree. So if I zoom in into this region of interest, I see that the immediate causes come from this component and this component. So as we know, from the diagram, that inert gas is being transferred from the TK1 component, from this tank, down the chain. And we see that if we cut off the net between this IV2 and IV3, IV3 by itself will not be able to have any access to the inert gas. And if there's no inert gas being transferred, then by itself, this component cannot produce thrust. And so by this reasoning, we come to the conclusion that the immediate and necessary condition is that for the both valves to be open at the same time. Then we ask whether, like, because we had also identified the third component that is being that is being connected to IV3 component, which is the relay switch. So the relay switch, it sends an electronic signal. So it is being, it does contribute to it can contribute to thrust being produced. However, it does not provide inert gas. So it's not an immediate cause. Since it's not an immediate cause, we only end up with IV2 and IV3 uh, conditions being open. And so if we go back to to our design, I go back to the fill effect. I list these two conditions, these two causes: isolation valve IV2 and isolation valve IV3 remain open after cutoff. And I create these two events by going into the intermediate effects and then specifying them in this window. Isolation valve IV2 remains open after cutoff, and isolation valve IV3 remains open after cutoff. After specifying these two descriptions and then listing them as causes for the top event, I can then rerun the Fimica and generate my fault tree down the branch. So once I zoom out, I see these two descriptions contributing to the top event. Isolation valve IV2 remains open after cutoff, and isolation valve IV3 remains open after cutoff. Finally, let's say we want to go down this part of this branch. Isolation valve IV3 remains open after cutoff. So how would we go about, generating fault tree next? So the next step would be to identify the system level cost and the component level cost. So the system level cost I identified as, so as IV3 providing thrust. So for instance, I listed isolation valve IV3 remains open after cutoff. If I go back to this intermediate effect, isolation valve remains open after cutoff. I list two causes. I list one state cause, as EMF continues to be supplied to IV3 after cutoff. And then the second cause is the component fault cause. It's a primary failure of IV3 to close after cutoff. So in order to specify the system costs, all I have to do is I have to provide this description over here. EMF continues to be supplied to IV3 after cutoff, which I had done over here. And then I listed this as a cause. And then for the second one, which is a component failure, primary failure of IV3 to close after cutoff, what I have to do, I have to specify this failure effect for component IV3, in a component IV3. Once I choose this component and the failure effects, I put this description: primary failure of IV3 to close after cutoff. And then I have to specify from my failure modes, I have to specify the causes. which I specify contamination, corrosion, structural failure. So, and in order to specify that, I go into the failure modes tab, and then I input these descriptions. So once I create these three descriptions, I include them as possible causes. And then I include this failure effect, object failure effect as a cause. After I had done that, I rerun my Fumica, I generate my fault tree, and then if I go down the branch, I see these two descriptions. One is the system type event. Its EMF continues to be supplied to IV3 after cutoff. And then this is the component cause. Primary failure of IV3 to close after cutoff. So now if we close out of this Fumica report, because I want to show you how I generate this thing automatically. So in order to rerun this, what I had to do after supplying all of the necessary information, all of the intermediate effects, all of the necessary causes, all of the component uh, failure effects. For instance, let's say like this one has a failure effect, and then I provide failure modes. After I had inputted all of the necessary information in order to run, in order to generate a fault sheet, I run a Fumica report. In order to run a Fumica report, I click on this button. It asks me whether I want to create a new Fumica study. So I click yes. So on the hierarchy, I specify all, and then I click on the run button, generate Fumica. So after generating the Fumica report, I see the output of all the events, all the items that were included, all the failures that were specified, all the root failure mode causes, local and item effects. After that, in order to run the Fumica, I double click here. And so here it shows me the whole final output of the fault tree. And so in order to, like, if, for instance, this fault tree lists, failure rates. Like if I don't want to see this failure rates, first of all, like I can display this FTA with, it has three options: as modeled, like I can display it as simplified, or I can display it as optimized. And then I have an option if I don't want to see any failure rates, if I just want to see a qualitative fault tree, I click on this button, and then it shows me a qualitative fault tree. So there were a couple of things that I wanted to point out. So for instance, for this event, it has like an AND gate. And so it says here, EMF continues to be supplied to K3 after cutoff. And the two events that are being connected to the AND gate are the emergency switch S3 fails to open after cutoff, and then the primary failure of K6 to open after cutoff. So if we go back to our design view, this is the like the top event in question, the object arming relay K3, and it has causes of either S3 switch being not working properly, or the K6 timing relay not working properly. And these are being specified as end events. And so the question we want to find out, why are they being specified as end events? And in order to do that, what I had shown you previously, I had shown you one, diagnostic study, which was normal. And then the one that I haven't shown you is the emergency. So if we go back to the normal diagnostic study, we see, the components that are being suspects. So we see the K3 is being shown as a suspect, and then K6. However, S3 is not being shown as a suspect for the normal mode. But then if I go to my emergency test set, I see that the K3, K6 is not being suspect. However, the S3 component is being included. And so this is the reason why these two objects are being listed as end events. They have to happen at the same time in order for this event to fail, for this component to fail. So I just wanted to show that. And then the other thing that I wanted to share with you is that this particular object, K4, is not being shown in the fault sheet, even though it shows to be suspect in both diagnostic windows. So this just means that this component is not being listed as immediate, necessary, and sufficient cause in order to be included. And the reason why it's not necessary to include this component into the fault sheet is because if we go back to our modes, for instance, like in thrust mode, it has to be working. But then we see if we cycle through after transitioning to dormant mode, it supplies it supplies a signal to K3. So basically, it's not necessary to include this component because it does not play a necessary and sufficient role in order to be included into the fault sheet. So basically, this is a quick rundown of how I would create a fault sheet from the topological model. Thank you for your attention.